In this video, we're going to look at transformations applied to the reciprocal function. Let's just start with taking a quick look at the reciprocal function itself. It's y equals 1 over x. If we were to graph this, we would get very quickly part of a curve like this. We go through 1, 1, and part of the curve on the other side looks like this. We go through -1, -1. We have some asymptotes here. We have a vertical asymptote at x equals 0. We have a horizontal asymptote at y equals 0. The domain is the set of all x such that x is not 0 and x is a real number. The range is all y's that are not 0, where y is a real number. And there are no x-intercepts here. There's no y-intercepts here. None and none. And that's it. That's a quick sketch of y equals 1 over x, which is the reciprocal function. Now, what we want to be able to do is apply transformations to reciprocal functions and see where these critical points, 1, 1 and -1, -1, will move to. And of course, there's other critical points as well. If we wanted to keep track of more than just those 2 points, we could look, for example, at 1/2, 2. That's on the reciprocal function. We could look, for example, at -2, -1/2. That's on the reciprocal function. We could keep track of any points we wish. 2 of the main ones, though, are 1, 1 and -1, -1. And that will help us see what's going on. So what I'd like to do now is go through and look at some transformations and see what they look like in function notation and not in function notation for a parabola, for a parent curve f of x equals x squared, and also for the reciprocal function f of x equals 1 over x. So let's start with y equals 2 f of x. And what transformation does this give us? Well, we have the original function, whether that original function is x squared, or whether that original function is the reciprocal function, or whether that original function is some other function altogether. Doesn't matter. What's happening is the output of the function, the y value, is being multiplied by 2. So we're going to get a vertical stretch by a factor of 2. All the y coordinates on our parent function are being multiplied by 2. What would this look like if f of x here was x squared? Well, the equation would be 2 times x squared, y equals 2x squared. This, without the function notation, you probably recognize as being a parabola that's been vertically stretched by a factor of 2, because this 2 here is in the place of a. What would happen to our curve? Well, 0, 0 would remain right where it is, because when we multiply the y coordinate by 0, it would have no effect. Sorry, by 2, it would have no effect because it's 0. 0 times 2 is still 0. What would happen when we transform 1, 1? Well, we would get 1, 2 because we're multiplying the y coordinate 1 by 2. And so that point would shift up from 1, 1 to 1, 2, which would make the original parabola gets steeper. That's the vertical stretch. All right, well now, what about with f of x equals 1 over x, the reciprocal function? First of all, what would that equation look like? Well, our function y equals 2f of x is saying whatever f of x is getting multiplied by 2. So a reciprocal function that's having a vertical stretch by a factor of 2 would be y equals 2 times 1 over x. And 2 times 1 over x is the same as 2 over x. So if we saw this function here, y equals 2 over x, we would know that in fact this is the same as y equals 2 times f of x, where f of x is this parent here of 1 over x. And what would happen to these two key points? Well, when we vertically stretch -1 comma -1 by a factor of 2, the x-coordinate stays the same because it's a vertical stretch. The y-coordinate gets multiplied by 2, so it gets a little bit lower. What would happen with 1, 1? Well, the x-coordinate stays at 1, but the y-coordinate, which is multiplied by 2, becomes 2. So this is what would happen when we have a vertical stretch by a factor of 2. And we could take a look at other equations, other parent functions, and we would have a similar effect. Y equals 2 times f of x is a vertical stretch by a factor of 2, no matter what f of x happens to be. Let's take another one. Let's suppose now instead of a 2, we have a k. Y equals k f of x. What's this? Well, this is a vertical stretch by a factor of k, whatever k happens to be. What would that look like if f of x was x squared? Well, replace this f of x with x squared. We have y equals k x squared. How about for the reciprocal function? Well, we would have k times 1 over x. And k times 1 over x is k over 1 times 1 over x. Multiply those fractions or rational expressions, and you get k over x. With the parabola, where would 0, 0 get transformed to? Well, we would multiply the y-coordinate by k. 0 times k is still 0, so it wouldn't move. What would happen with the 1, 1 point? Well, the x-coordinate would still be 1. The y-coordinate, 1, would become k, because we'd be multiplying by k, and 1 times k is, of course, k. What would happen? What would be the transformation when we're applying this vertical stretch by a factor of k to the reciprocal function? Well, -1 for the x-coordinate wouldn't change, but the y-coordinate would get multiplied by k. It would become -k. How about 1, 1? Well, the x-coordinate wouldn't change because there's no horizontal stretch or compression, but the y-coordinate would be multiplied by k. And so we would end up with that point there. All right. Now let's take a look at what would happen if we had y equals f of x plus 1. Well, here, f of x is the output of whatever function we have, and then we're adding 1 to it. So we are increasing y's value from whatever it normally gets after this function is applied. We're taking that output and then we're increasing y by 1 more. So we're going to have a vertical translation up by 1. Now, what would the equation look like for f of x equals x squared if we had this transformation? Well, f of x is x squared, so we would have y equals x squared plus 1. This is the equation that is f of x plus 1, where f of x is equal to x squared. How would this affect 0, 0? Well, the x isn't being affected at all. The y, though, is having 1 added to it. F of x equals x squared gives an output of just 0 when x is 0, but then we're adding 1. So we end up shifting that point. 0, 0 gets transformed to 0, 1. How about 1, 1? Well, 1 is the output once f of x has been applied, but then we're adding one more 1. So x, of course, doesn't change, but y becomes 2. We're shifting the curve up by 1. You can see 0, 0 is now 0, 1. 1, 1 is now 1, 2. Both points have gone up by 1. Okay, well now let's take a look at this again. Y equals f of x plus 1. What does it look like when f of x is 1 over x? Well, it's 1 over x, that's our f of x, plus 1. Now, notice that we could see this in a different form. We could, for example, see y equals x plus 1 over x. That is the same thing, just in a different form. So sometimes it can get a little bit tricky when we're given an equation to figure out what is this in terms of a transformation applied to f of x. Because here, of course, this is the same as x over x plus 1 over x. X over x is 1. And so here we have it, f of x plus 1. If I gave it to you in this form, you might not immediately notice that this is actually the reciprocal function plus 1. But it is. Okay, let's get back to y equals 1 over x plus 1. How about these points? What would happen? Well, just like with the parabola, we're just adding 1 to the y values. So -1, -1 would become -1, 0. 1, 1 would become 1, 2. Let's take another example. Let's suppose this time we have y equals f of x plus 1. Now this is different. This is the first time I've taken my function y equals f of x and altered the argument to the function. I've altered what goes into the function. The other times, the first 3 examples, I altered what happened after the function already gave its output. That means that in those first 3 cases, I'm altering the y direction, the vertical direction. But this time, it's a little bit different. This time, I'm altering the input. So I'm therefore altering the x direction. Now, this is x minus -1. So what's happening here is a horizontal translation to the left by 1. Okay, because we're subtracting a -1. What would this look like in terms of an f of x equaling x squared? Well, f of x plus 1 means everywhere we see an x, we replace that with x plus 1. So I have y equals f of x plus 1, where my f of x is x squared. That's x plus 1 squared. So if I saw this function, I could interpret that as being y equals f of x plus 1, where f of x is x squared. In other words, if I saw this, I could interpret this as being a translation horizontally to the left by 1, applied to the function x squared. All right. So now the question is, how are the points 0, 0, and 1, 1 transformed? Well, in each case, we have a horizontal translation 1 unit to the left, so the 0 for the x would become a negative 1. The 1 for the x would become a 0. So this is how we would have our transformation. How about if f of x was 1 over x instead? Well, y equals f of x plus 1. Everywhere you see an x in f of x, you replace it with an x plus 1. That's what the function notation says. So I have y equals 1 over x plus 1. What is this telling me? Well, this is saying if I see y equals 1 over x plus 1, then that's equivalent to y equals f of x plus 1, where f of x is 1 over x. In other words, this is a reciprocal function with a horizontal translation left 1. How would that impact negative 1, negative 1? Well, negative 1 would go 1 to the left. I'd get negative 2, negative 1. How would that impact 1, 1? Well, the 1 would go left by 1. I'd get 0, 1. Notice, by the way, in the third and fourth line, when we look at our transformations on the reciprocal function, we have intercepts. So now, in the third line, for example, I have a negative 1, 0. That's an x-intercept. And in the fourth line, I have a y-intercept, 0, 1. So we can have intercepts for the reciprocal function. It's just that we need to shift that function in order for that to happen. All right, let's take another example. Let's look at y equals 3 f of x minus 2. What's happening here? Well, this time we have two transformations being applied at the same time. We have an x minus 2 in our input, which means we're shifting right by 2 horizontally. And then we're also taking the output of our function f and multiplying that by 3. That impacts the y. It stretches the y by a factor of 3. So we have two things here, a vertical stretch by a factor of 3, and also a horizontal translation to the right by 2. To the right by 2 because we're subtracting 2 from x. Okay, so this is our general function with those transformations. What would that look like in the case of a quadratic? Well, let's look at f of x minus 2 first. That's saying everywhere that I put an x, I'm going to have to replace that with an x minus 2. So that is f of x minus 2. But then f of x minus 2 is being multiplied by 3. So that is the function we're looking at. You know, and like I mentioned earlier, this could be written in a totally different way, right? This could be y equals 3 onto x squared minus 4x plus 4. Y equals 3x squared minus 12x plus 12, right? So we might see that and not recognize at first what's happening. We might see that and factor out a 3 to get to the line above it, and then factor that and say, oh, I see what's happening. This is two transformations applied to the function f of x equals x squared. Okay, so sometimes it takes some work to get it into a form that's recognizable. But once you have it in a form that's recognizable, you can see quite clearly what sorts of transformations are being applied. All right, so where would 0, 0 go? Well, 2 to the right, and the y-coordinate is being multiplied by 3. Well, that has no effect on 0, so 0, 0 goes to 2, 0. What about 1, 1? Well, the 1 in the x-coordinate is going 2 to the right, so that becomes 3. And the 1 for the y-coordinate is being multiplied by 3, so that also becomes a 3. So 1, 1 goes to 3, 3. What about if we were looking at the reciprocal function? Y equals 3f of x minus 2. Well, f of x minus 2 says everywhere we see an x, we replace it with an x minus 2. So if f of x was the reciprocal function, we would have x minus 2 and a 1 there. That's f of x minus 2. But then f of x minus 2 is being multiplied by 3, so instead of having a 1 in the numerator, we have a 3. So if you were to see y equals 3 over x minus 2, you should look at that and be able to see, okay, well, the x was replaced with an x minus 2. So I have an f of x minus 2. And that would be a reciprocal function, like that, except there's also this 3 here. So I guess my f of x minus 2 has been multiplied by 3. And once you can do that, once you see this and you can see that it's this function where f of x is 1 over x, then you've got your transformations. Then you can see what kind of transformations are being applied. How would these points move? Well, the x-coordinate of negative 1 would go right to, it would become a positive 1. The y-coordinate of negative 1 would be multiplied by 3. 1, 1, well, the x-coordinate of 1, we add 2, it becomes a 3. The y-coordinate of 1 gets multiplied by 3, it becomes a 3. Let's look at another one. This time, let's take a look at y equals 3f of 2 onto x minus 1. Now we have 3 parameters. What's going on here? Well, we have an x minus 1, so we are shifting right by 1. We have a horizontal translation to the right by 1. What else is happening? We're multiplying x minus 1 by 2. What effect does that have? Well, we have a horizontal compression by a factor of 1/2. Remember, if we use the notation that this is q, for example, is 1 over q that is multiplying our x-coordinates, not q itself. So it's 1 over 2 that's multiplying the x-coordinates, not 2 itself. And because 1 over 2 is less than 1, it's a compression. The name matches what's happening. When we're multiplying by a number less than 1, that compresses the curve, so it's a horizontal compression. But we're not done yet. After f of 2 onto x minus 1, we're still multiplying by 3, so we additionally have a vertical stretch by a factor of 3. All of this is happening. Well, what would this look like with y equals x squared? Well, the argument is being replaced with a 2 onto x minus 1. So if f of x equals x squared, this inside part is going everywhere we see an x. So we have 2 onto x minus 1 squared. Then what? Well, the output of this function then is being multiplied by 3. So there is the equation of what's going on. Now, this could look many different ways. We could distribute the 2 on the inside. There's lots of things that could happen to make this look different. But going straight from the function to the quadratic, that's what we have. What would happen with our transformations? Okay, now we have to be careful here, because in the horizontal direction with the x's, we have both a compression and a transformation. How do we deal with that? Well, we must always use the order of operations. So we're going to multiply by a half first, then we're going to add 1. 0, 0. Multiply by a half first, 0, then add 1, 1. And in the vertical direction, we're stretching by 3, so 0 times 3, that's still 0. Let's do it again with 1, 1. Horizontally, we have two things happening horizontally, a compression and a translation. The compression means I'm going to take that 1 and multiply it by a half. That equals a half. Plus 1, 3 halves, or 1 and a half. So first I'm taking 1, I'm multiplying it by a half, then I'm adding 1 more. That's how I get my 3 halves. What about the y coordinate? Well, only one thing is happening to the y, is a stretch by a factor of 3, so 1 gets multiplied by 3. That's the y coordinate. What would this look like with a reciprocal function? Well, everywhere we see an x, it's being replaced with a 2 onto x minus 1. So that is 2 onto x minus 1. Then the output is getting multiplied by a 3. So that's what we have there. Okay, you're going to need to practice looking at something like this and figuring out what is the function, reciprocal function, and what sort of transformations have occurred. Well, this entire thing has replaced my x, and this is a vertical stretch applied at the end. Okay, so now what would happen to transforming these points? Well, in the x direction, first I have to do my compression by a half, so this negative 1 becomes a negative a half. Then I have to add 1, so it becomes positive a half. How about the negative 1 in the y coordinate? Well, only one thing is happening. We're multiplying by 3, so it becomes a negative 3. So negative 1 gets transformed to the point 1 half comma negative 3. How about 1, 1? Well, in the x direction, the x coordinate, we have to multiply by a half and then add 1 for the transformation. So when I multiply by a half, I get a half. When I add 1, I get 3 halves. How about the y coordinate? Well, that 1 gets multiplied by 3 because of the vertical stretch. So that is what happens when we apply transformations there. All right, let's get another one here. This time, let's take a look at y equals 4 f of 2x minus 2. Now, this is a little bit tricky. You must notice that I do not currently have inside my f of x the form q onto x minus h. And we can't read off the transformations unless and until we're in that form. So this here must be seen as 4 times f of 2 onto x minus 1. I have to factor out that 2. Otherwise, I'm going to have the wrong transformations. Simple as that. So now that this has been factored, it's pretty straightforward. We have a horizontal shift, a translation right by 1. We have a horizontal compression by 1/2, because I take the 2 and I take the reciprocal of it. And we have a vertical stretch by 4. So in fact, this will be very similar to the previous example. How might it show up? Well, part of my reason for having this one is to show that it could show up as y equals 4 onto whatever you see in the brackets is replacing x. So x squared, the x in x squared is replaced with 2x minus 2. Right? It could show up like that. But if you see that, you're going to have to factor out the 2 on the inside in order to identify what all your transformations are. How would that play out with the points? Well, 0, 0. We compress by 1/2 horizontally. That's still 0. We add 1. How about the 0 for the y? We times it by 4. That's still 0. 1, 1. The 1 gets multiplied by 1/2 to 1/2. Add 1. That's 3/2. The 1 in the y gets multiplied by 4. There we are. How could we see it with the reciprocal function? Well, we have y equals 1 over 2x minus 2. Everywhere you see an x, replace it with 2x minus 2. Times that by 4, so you have a 4 like that. And again, my point is, if we had that function, we would have to factor out the 2 in the denominator in order to identify what transformations are taking place. If you want, go ahead and figure out what the transformations will be on the points -1, -1, and 1, 1. Here's the next one. Y equals 4 f of 2x minus 3 minus 5. Now you'll see here that we have all 4 parameters at play. Not only that, but inside the argument to f of x is not currently in the form q onto x minus h. So that 2 needs to be factored out in order to get the correct horizontal translation. Moreover, factoring out a 2, I mean, it's not the end of the world, but it's not super pleasant. So we have 2x minus 3. How do you factor out a 2? Well, you need to have here whatever you would times by 2 to get to 2x. That's clearly an x. Here, 2 times something equals 3. Or in other words, 3 divided by 2 is what goes there. So I have 3/2. Double check, 2 times x, 2x. 2 times 3/2, that is in fact 3. So I've got it correct there. So in order to properly see what's going on, I need to rewrite the argument to my function as 2 onto x minus 3 halves. And then outside of that function, I still have a minus 5. So let's put it all together here. What's going on? Let's look inside the function. Inside the function is my x. So inside the function, I have a horizontal compression by a factor of 1/2. Why a compression? Because we take the reciprocal of that too. I also have a horizontal translation to the right by 3/2. Why to the right? Because we look at what's being subtracted from x. Also, after the function, I'm multiplying my y, because f outputs a y. But that y then gets multiplied by 4, so I have a vertical stretch by 4, and then we subtract 5. So I also have a vertical translation down by 5. Those are all of the things that are happening there. What might this look like with a parabola? Well, for a parabola, let's go back to the original one. I would have y equals 4 onto, what's the argument? 2x minus 3 is the argument. Anywhere you see an x in x squared, we replace it with 2x minus 3. And then a minus 5. If I saw that, that would mean that I have a horizontal compression by a factor of 1/2. I'd have to factor that 2 there in order to see exactly what my horizontal translation is. I could see now it's going to be a 3/2.